This presentation is about a recent work in collaboration with Michael Różański and Christian Ye, who has also prepared a poster. So I will try not to give a super technical talk. It will be about hyperbolic Cauchy problems with multiplicities. So this is the plan of the talk. Okay, so now I cannot go. Here we are. Okay, so we'll start with some motivation introduction. In particular, I will fix some notation so that we all have the same kind of language. Then I will try to summarize a little bit of the history of this problem, and we will see that many results are known when the coefficients are depending on time only, but the research has not been as well successful when the coefficient depend on x as well. And our result is about the general t and x dependent case. We obtain some results of Sobolev posedness and also some representation formulas. So here we go. All right, so let's start by fixing some language. Okay, so I will talk about hyperbolic Cauchy problems with multiplicities, and an expression which is also used in the literature is weakly hyperbolic. What does that mean? So here we have a m-order differential equation, okay? So I will use the standard notation for the derivatives, so d alpha, where we have the imaginary unit here to the length of the derivative, okay? So here we see an equation of m order, and we have here some differential operators of order n minus j. At the moment, I'm not putting any special assumptions on the coefficients, right? I will be more precise later. So when do we say that this equation is hyperbolic? So we consider the corresponding characteristic polynomial. Basically, we take the principal part of the operator, and then we consider the corresponding symbol, and we will get an expression of this type. So I guess this is quite well known to everyone. And then I will look at the roots of this polynomial with respect to tau. And we say that the corresponding equation is hyperbolic if we get real roots. So now these roots might be distinct or they might coincide. And when they coincide, we say that we have an hyperbolic equation with multiplicities. And this is the case that I'm interested in. All right, so this is a workshop on pseudo differential operators. So you might ask, okay, so but what is the link with a pseudo differential operator? And it is actually very clear. So instead of studying directly this equation and then the corresponding Cauchy problem, it is quite standard to make a transformation of this equation into a system, a first order system, but we will not have any more differential operators, we will have pseudo differential operators. And the transformation is quite standard. It is done by using this kind of pseudo differential operator, which has the symbol given here by the Japanese bracket. So this is the expression, okay? Then I will, so if I have an equation of m order, I will get a system where the size of the matrix is m times n. How do I do this? Making use of this transformation. So I will define uk as the time derivative, the k minus 1 time derivative, and then I will have this pseudo differential operator acting on u, and this is of order m minus k. All right, so when I do the transformation, right, I will get a matrix here, which is of a special type. It is in Sylvester form. And we use this expression because we have this special structure. So you see, you have a lot of zeros, okay? And then just the last row will have entries here, which are in principle different from zero. And there is there are precise formulas that will relate the entries here, Bj, with the coefficients of the equation. So this is the formula. And clearly when you do the transformation, you have to do it everywhere. So also you need to transform the initial data and the formula is given here. So if you've done your transformation correctly, then you will have that the roots of the characteristic polynomial, so the m roots that we have here, are actually the eigenvalues of the symbol matrix, right, of this operator here, actually of the principal part of this matrix. So how can we see this? I have written here, to be very clear, what are the symbols of the matrices that we have seen before, okay? And I have made a distinction between the principal part and the lower order terms. So we are working with symbols here, and these will be symbols of order 1, and this will be a matrix of the lower order term, and these will be symbols of order 0. And if you compute the eigenvalues now, the matrix A, you will find the roots of the equation that we have seen before, right? Okay, so dealing with higher order hyperbolic equation basically means to deal with a system, an hyperbolic system of pseudo differential operators of the first order. All right, so yeah, so if you have any question, please just stop me in case. All right, so let's have a little bit of history now. Okay, clearly it's a huge topic. There are many people in this audience who are probably more expert than me on this, right? So you might see that actually I will miss some references, so apologies about this. But it is actually a huge area of research and analysis, and there are still many open problems, right? And it is particularly challenging to understand hyperbolic equations when they have multiplicities. So we basically know everything when an hyperbolic problem does not have multiplicity, so it is strictly hyperbolic. And this goes back to Hermander and many other authors, but it is not the same when we have multiplicities. And we can already start to look at a very simple example. So here we have, in example 1, apparently a very nice equation. So it's a wave equation, but we have a coefficient here, right? So a coefficient, a variable coefficient, depending on time and on space. And I will assume, in order to have an hyperbolic equation, that it is positive, but that it might also have zeros. So up until now, there is no characterization of smooth functions A for which this problem is C-infinity well posed. So we would expect somehow C-infinity well posed then, because this is what happens when we have a strict hyperbolic equation. But unfortunately, this is not true when we have multiplicities. So what have different mathematicians done to try to understand this problem? So they have tried to find sufficient conditions, yeah, on the coefficients A in order to have a C-infinity well posedness. They had quite a success, for instance, on a second order equation, but it is actually not clear what happens in general when we have an M order equation. And I will mention here, sorry, somehow there is a strange noise. Okay, so I cannot, okay, right. And there is quite a famous result by Olenek in the 70s. So she produced some sufficient conditions on the type of equation that I mentioned before. So actually a second order equation also with lower order terms in order to get C-infinity well posedness. So the condition is of this type, if I formulate it for the equation in the example 1. And in particular, we can see that if the coefficient does not depend on x, then this becomes quite a simple condition on the coefficient A and on its derivative, okay? But we don't know actually what happens when we have an higher order equations. And also, we have a result of no C-infinity well posedness. So if we drop Olenek's condition, then it might happen that we do not manage to get C-infinity well posedness, and we do not even have a distributional solution. And this has been shown in an old paper by Colombini and Spagnolo in '82. So they prove that there exists A, which is C infinity, depending on time, and initial data G1 and G2, which are also smooth, such that the Cauchy problem before does not have any distributional solution in this sense. So you might ask, okay, then what happens, right? So where do you get well-posedness? Okay, the answer is yes, we can get well-posedness in some suitable spaces. And there are many results of Gevrey well-posedness. I will not recall here the definition of the Gevrey classes. I will simply say that these are intermediate classes between analytical function and smooth functions. So there have been quite a production of papers about Gevrey well-posedness of weakly hyperbolic equations, in particular when we have t-dependent coefficients only. There has been quite a work in the Japanese mathematical community, but also in the Italian community in Pisa. They started from second order equation with t-dependent coefficients, then they went to analyze higher order equations, and they use different techniques like symmetrizer, but also a perturbation of the symmetrizer called quasi-symmetrizers. But there are many less results when we have t and x dependent coefficients. There is a famous result by Bronstein in '82, which has been extended then by Oya et Arama later on. But the assumptions, the coefficients are quite strong. So they require Gevrey dependence in x, and they can be, let's say, less regular in t, but anyways, you cannot go below order in t. Okay, so when many years ago, when I started to work with Michael at Imperial, we got interested in this kind of problems. So I have just listed here some of our papers. We have started from the t-dependent case, and we have also considered a range of regularity in the coefficients from a smooth coefficient to less regular coefficients, older of even distributional coefficients. So there are some papers here, but there is also a reference list at the end of the talk. And if you have any question, you can just ask me. All right, so I believe this is the end of the general introduction. And now let's focus on the core of this presentation, so the problem that we have studied. So this problem has been studied starting from 2018. So the results have been published in 2 papers. There is a first part where we prove well-posedness, and then there is a second paper where we have proven some results of propagation of singularities. So we have done some microlocal analysis. All right, so this is the problem that we are interested in. So it is a system, all right? So I will have here a first order system of pseudo-differential operators, okay? I will have a matrix A, which is a M times M matrix whose entries are pseudo-differential operators of order 1, and then I assume continuity with respect to time. And then I have a matrix B, which is a matrix of lower order term, and they will be pseudo-differential operators of order 0. I also assume that I have an hyperbolic system, which means that when I consider the symbol of the matrix A and I compute its eigenvalues, these are real. So I will get M real eigenvalues, which might coincide somewhere. So I will have multiplicities. So our starting point has been a paper by Gramchev and Ruzhansky in 2013, where they studied this problem, but with only a 2x2 matrix. Okay, so in that particular case, via some technical procedure that they applied in details, making all the computations, they proved that this Cauchy problem is Sobolev well-posed, okay? So they had some results of Sobolev well-posedness and also with some loss of derivatives. So in the end, they used some anisotropic Sobolev spaces. The main point of this paper was basically to transform the matrix A into upper triangular form. So I will recall later on what is this transformation, because that was our starting point and it inspired us to get then a general result. So we wanted to understand if it was possible to extend this result to matrices of any size. And the answer is yes, right, as expected. But clearly we needed to understand very well which were the hypotheses needed on A in order to be able to perform this transformation into upper triangular form. So it turns out that in the 2x2 case, it is quite easy to understand when a matrix can be reduced in upper triangular form. And mainly if one look at the paper, then the condition that Gramsci and Rózsansky found is of this type. Okay, you can find an eigenvector which has one component which is always different from 0. So you have to understand that the eigenvalues and the eigenvector depends on t, x, and c. So you need that there is a certain component of this eigenvector which is always different from 0 independently of t, x, and c. All right. So we expected, okay, we might be able to find a similar hypothesis on the eigenvectors. So the answer is yes, but it becomes much more technical. So in the first paper where we proved the well-posedness of this Cauchy problem, we actually had quite a big appendix where we wrote down all the hypotheses we needed to perform this transformation into upper triangular form. So I will not give you the details today because I don't believe it's actually a good idea in a talk like this one. And for simplicity, I will assume that the matrix A is already in upper triangular form. And then I will discuss how we find well-posedness. And again, in order to make this talk as clear as possible, I will assume that my matrix A is a 2x2, okay? Because in this way we can understand mainly what we are doing. And I will make use not of the theory of pseudo-differential operators, but I will make use of the theory of Fourier integral operators. So let's have a look. All right, so I have rewritten here our toy model, which is the 2x2 example. All right, so we will have the matrix A that we assume to be in upper triangular form. So I will see the eigenvalues here, λ1 and λ2. Then I will have another entry here. So this will be pseudo-differential operators of order 1. Then I will have a matrix B, which is of pseudo-differential operators of order 0. Then I will have the column of the initial data, and then I will have the column of the right-hand side. And then we will see in which spaces to work, okay? So we will end up getting Sobolev well-posedness, but we will have to be a little bit careful about the order that we are choosing. Okay, so what to do now? All right, so mainly the idea is making use of the fact that we are in upper triangular form. We will be able to solve the second equation. So I will start from the last equation here. So I will solve it, okay? So I will find U2, and then I will plug it in the first row, and then I will find U1. So this is the idea. And you can also understand that this is a procedure that can be iterated, okay? Even if you have a matrix of a bigger size, but you still have this structure. So why we can do this? But clearly it helps us very much the fact that we have the theory of Fourier integral operators. So we are using classical results that I will briefly summarize, which basically tells us that in this situation, we are able to have an expression, to have a formula for the solution, and this will be given as as a sub-Fourier integral operator or integrated Fourier integral operator acting on the initial data and on the right-hand side. So to fix some language, I have recalled here some, in a nutshell, what we need about Fourier integral operators. So clearly this is very short, okay? More details can be found in the paper. So for each eigenvalue lambda j of the matrix, we denote with gj0 theta the solution of this Cauchy problem, okay? So it will depend on the initial data that I have here, okay? And it will be possible to compute precisely what is this operator. So this is a Fourier integral operator, so you can see it down there, okay? Where our phase function and symbol will depend on time as well, okay? And it is possible to compute precisely what is the phase function and also to find an asymptotic expansion for this symbol here. I will not only use this kind of operators, I will also use some integrated Fourier integral operators. So I will have an extra parameter S, and then I will integrate with respect to S as well on the interval 0t. And this is the solution of this other Cauchy problem. So it will act this time on the right-hand side G that I have here, all right? What are the properties of this operator? So as I said before, the phase function can be obtained precisely because it is the solution of this iconal equation, okay? And we will also make use here of this notation. So note that we have an extra parameter here, right? So we have S and also we have T. And it is also possible to find, to understand what are these symbols that we are using in these operators via some asymptotic expansion. So the question is, okay, we have this operator, so how do they behave? So what are the mapping properties? And the mapping properties that we are using are Sobolev mapping properties. So it turns out that these operators have symbols of order 0. So because of that, they will map HS into HS. So what is the difference between these two estimates? So the first one is just a Sobolev mapping property of a classical Fourier integral operator. In this other, we have an integrated Fourier operator, and that's why there is this extra T here, okay? But the mapping property will always be of this type. So I start with a Sobolev space of order S, and then I will end up in the same Sobolev space with the same order because of the fact that I have a symbol of order 0, all right? Okay. All right, so let's go back to our problem, okay, right? So this was the problem that we had at the beginning, so the 2x2 model. This is the matrix, okay? So now we apply all this machinery. So we apply this theory of Fourier integral operators, and then we found a precise way, right, to express U1 and U2. All right, so what are these? Okay, I start from the second equation. I get this expression, all right? So this will be a integrated Fourier integral operator, right? And there will be a composition with a pseudo differential operator, which comes from the lower order terms, right? If I look at the first equation, all right, I will also have this term, which is of order 1, and then again, I will have a composition between a Fourier integral operator and a pseudo differential operator. And these two terms here, U01 and U02, are a combination of the initial data and the right-hand side, and there are also these Fourier integral operators acting on them, all right? Okay. So once I have this, what do I do? So now I take 3, I take the expression of U2, and I plug it in the equation 2, and then I will just get an equation with U1. And you can guess now how we want to proceed. So basically, we want to apply a fixed point argument, okay? So to be able to find U1, okay? And once we have U1, then we can find U2. And this is a kind of method that we can iterate even when we have more equations. But we have to be sure that we can do this, right? So to be able to apply the Banach-Fins point theorem, so first of all, we need to be in a suitable Banach space. So you might think, okay, let's take a Sobolev space, but we have to be sure that that this expression here, right, will be in the right spaces. So the idea is, okay, so if I say, okay, U1 is in HS, so I have to be sure that this guy, after the composition with all these operators, this will still be in HS. The same has to be true for this term, and the same has to be true for this U tilde 0, 1, okay? So now let's analyze this term, and let's see if this happens, or if we need some extra hypothesis. All right, okay, so let me just go back 1 second, because I believe it is actually clear if I discuss it on this page. Okay, so these are symbols of order 0. These are Fourier integral operators with symbol of order 0. So if I start from HS, after the composition, I will still be in HS. So this term is totally fine. It does not give me any trouble. So what about this other term? Okay, so I start from HS, then I have a symbol of order 0, so I'm still in HS. The same is true when I apply G2, but now I have a problem here, because this is a symbol of order 1. So I will not end up in HS. So I see immediately that in order to have this Sobolev mapping property, HS into HS, I need to require that this lower order term is not only of order 0, is of order -1. And this is a sort of Levy condition, right? Which is actually not surprising when we have hyperbolic problems with multiplicity. We expect to need this kind of hypothesis. Okay, so I will require that this B21 is of order -1. And then if I look here at how this term is defined, then I will see again that, all right, so this will be a symbol of order 1. So if I want that out of this I get something in the Sobolev space HS, then I will need that this U02 is in HS plus 1. So I will also see immediately from 6 that I will have this sort of anisotropic Sobolev structure. So the components of the initial data to the right-hand side, and therefore the solution will not have the same regularity. So the second component will need to be more regular. We need to be in HS plus 1. So in the next page, I basically summarize what I just explained, right? So if we put this assumption on the lower order terms, and also this assumption on the second component of the initial data on the right-hand side, then everything will work out well. And then we will end up to be able to have a map, which is a contraction, and therefore we can apply the Banach-Fins point theorem, and then we can find a unique Fins point, and therefore a unique solution. So in principle, I will have to choose a smaller interval, 0t, but then I can repeat actually this argument, and then I can cover the whole interval 0t. All right, so this is the summary, right, of the structure of the proof, all right? Before stating the general result, because this is a result which is already proven by Gramchev and Ruzharsky, we extended this result to m times m matrices. I just would like to go back a second and to show you, to explain you what is this Levy condition. So basically we said that this term, which is the term which is below the diagonal, has to be of order -1. So you might ask, okay, but then what happens when you have a bigger matrix, when you have an m times m matrix? The Levy condition will be very similar. I will have a very similar structure. So I will take the diagonal of the matrix, then below the diagonal, I will assume that I have symbols of order -1, and then I will argue, going below, on line which is parallel to the diagonal. So I will have orders -1, then on the other diagonal below, I will have -2, and so on, until I cover the whole matrix. So this is the statement. All right. How much time do I have? Sorry, because
we are on time, I think.
We are on time, so how much do I have?
Yes.
Still?
1 minute, 2 minutes is good.
Okay, all right. Okay, so this is the general statement that we have proven with Michael and Christian in 2018. So you will see here that I require that the lower order terms Bij are of order j minus 1 when I is bigger than j. So this is the Levy condition that I was saying before. And then I will also have this anisotropic Sobolev structure. So I will have that the initial data and the right-hand side, the components k are of order s plus k minus 1. Under this hypothesis, then I can prove that there exists a unique solution U whose components are in this space. All right. Okay. So this is a well-posedness result. And our next step was to try to understand a little bit more the solution, right? So in particular, because we wanted to see if we could do some propagation of singularities, for instance, right? So if we could understand a little bit more what is happening also from a microlocal point of view. And to do this, we started by considering a previous work by Kamonsky and Rózsansky, where they got results of propagation of singularities for hyperbolic systems of pseudo-differential operators. But in their paper, they were assuming that the system was in diagonal form, so the matrix A was diagonal, and also they were assuming that the matrix A was depending only on X and not on T. So our work, our result, is basically a combination of this well-posed result with the analysis made by Rózsansky and Kamonsky. So we assume that A is now only depending on X, okay? And we try to understand that the methods that Kamonsky and Rózsansky used in the diagonal case can also be adapted to the upper triangular case. The answer is yes, all right? So I will try now to summarize what is this result. Okay, so you will see two sets of hypotheses. There is an hypothesis H1, which is necessary for the well-posedness. So it's the hypothesis on the lower order terms that I've just explained. And then there is a hypothesis H2, which is on the multiplicities. So this is what we need to get representation formula and then to be able to get the results of propagation of singularities. So what does this complicated hypothesis mean? So basically it is some intersection property. So we are allowing here involutive characteristic of a finite type, because we say that, okay, when I have a point of multiplicity, right, then if I iterate sufficiently enough the Poisson bracket at a certain point, I will get that this is different from 0. So there exists some n such that, and then you will have this assumption, all right? So this is what we need to be able actually to do microlocal analysis. So this is the statement, okay, which looks quite horrible when I look at it now, okay, quite dense. You can basically forget the first part, the first point, because this is just a summary of the well-posedness that we have discussed previously, okay? Let's try to understand the novelty of the second point. So what does this mean? So it means that for every n, we can write the components of the solution U as the action of suitable operators on the initial data and the right-hand side. So what are these operators? These are integrated Fourier or Fourier integral operators of order L minus J. So the operators H and K will be of Fourier integral operators type and will have order L minus J. So they will have these mapping properties. They will map HS into HS minus L plus J. But then I will also see a part which is regularizing, because R and S, they improve the Sobolev order. So if we start from HS, then we will end up in HS minus L plus J plus N. And I can do this for every N. So you can imagine that then when I want to compute the wavefront set of U, somehow I will disregard the regularizing part, and I will just look at the operator H and K. And here, the theory of Fourier integral operators will help me, because there are results which are already known in the papers by Amanda, where I can see clearly what happens. So what is the wavefront set of the operator H and the wavefront set of the operator K? So I will end up to have a result on the wavefront set of U, which is linked to the wavefront set of the initial data and the right-hand side. Okay, so I would like to conclude by stating this result. Clearly, this is just a statement. There is no proof, because I do not have time for the proof, and also it will be too technical. So this formula summarizes what I just explained. So the wavefront set of Uj is the union of the wavefront set of this term acting on the initial data and the wavefront set of this other term acting on the right-hand side. I am cheating a little bit here, because you might ask, okay, but then what are these two wavefront sets, right? So I would like to understand what is this. Okay, so this is the propagation along the broken Hamiltonian flow of the wavefront set of the initial data and the right-hand side. So why I'm talking on broken Hamiltonian flow? Because let's remember that we are in presence of multiplicities. So then if I travel along a bicharacteristic, then when I will meet another one, I will actually switch to that one, okay? And continue there, and then at another crossing, I will switch again, and so on. And this will give me this broken Hamiltonian flow.
Professor Garetto, maybe.
All right, we are done. Okay, so just to conclude, this is the references, and the two papers that I mention all the time are the last two here. Thank you very much.
Thank you very much, Professor Garetto, for your very nice talk.
Thank you.
We are open for questions.
I do have a question, if I can.
Yeah, sure.
So in the toy model, which is in the case of the 2x2 matrix,
yeah,
and also in the general case that you analyzed together with Michael Różański.
Yeah.
So essentially the structure of the matrix it's really important. So you need to have an upper triangular matrix. But are there, I don't know, either positive or negative results if the matrix doesn't have this structure?
No? I don't know at the moment. I mean, we have tried to find this sufficient condition in order to be able to transform, right, the matrix. But in general, I don't know. Right?
Not even in the toy model case, let's say the 2x2 case.
But I would expect that if you lose this structure, things might be actually much more complicated, right? Okay. So I would expect that maybe you will need other conditions.
Yeah.
So sure. In general, it's quite a challenging problem. There are some results of Parmigiani, for instance, and Parenti, right, where they have some extra assumption on the multiplicity, so there is some geometry behind, okay? One might also use some geometrical approach different from this one, right? I believe there are the results where they use this sort of geometrical assumption are usually only with X dependence and not with...
indeed, the problem is always that.
Yeah, it's always,
Yeah, okay, thank you.
Okay, thank you. Another question?
I would like to ask something. I know we're short on time, but so Claudia, I saw that recently you put online a preprint where you work with very weak solutions. So but this is related to this. I mean, this relaxation of the regularity of the coefficients and the right-hand sides.
So in this case, no, right? Okay, I have the door. So in this case, let me just 1 second. 1 second, okay? 1 second.
Yes.
Sorry, I'm back. All right, so in this case, the coefficients are smooth, right?
Mm-hmm.
And you need smoothness because you are heavily using the theory of pseudo differential operators and Fourier integral operators, which needs smooth symbol, right? You could, in principle, deal with singular coefficients, but then you will need to do a regularization. Then you will need to work with operators depending on a parameter, okay? And there is a lot of work which needs to be done because you will need, for instance, to understand, right, how the parameters is behaving in the mapping properties and so on.
But I think you're an expert. I mean, with all your experience from Colombo theory, maybe.
Yeah, okay, but it is quite, technically it is quite heavy, and you might need to put some extra assumptions. You might need some boundedness with respect to epsilon, which actually might restrict the family of problems that you can deal with, these kind of things, right? But in principle, yes, one could think to do it, right?
Thank you.
Okay, thank you. Other questions?
May I ask a question? Do you have a specific example that you would like to understand where these conditions are met?
I believe there was an example that we wanted to put in the paper, but in the end we didn't do it, which was from elasticity, I believe, right? But our interest started from a very, how can I say, theoretical, right, approach. Also because we wanted also to extend the paper by Różański and Kamowski, where they were using this assumption of diagonal system, right? Which looked a little bit too restrictive, right? So definitely what you can do in that case can be done with some adaptation if your matrix is in upper triangular form. Yeah.
Thanks.
Thank you.
Okay.
Sorry for disappearing, but there was someone at the door.
Okay, so thank you very much, Professor.
Thank you. Thank you.
Participation.